Um, I need to. I had a good cold open thing that I have now forgotten, which is a real bummer. Because
what's a computer? What's an operating system? What's a programming language? Who are you? Why are you in my home?
that's exactly it. And today in Sean's home, you will find me, Joseph Marlin, co-host of. We screwed this up last time, and I was just about to do it again. Adjunct of Computing. Welcome everyone. Yet again, we've managed to make it a couple episodes now, and it's going great. So thank you for tuning in. Today, we are talking about old computer things. And in specific, this is covering where I just went over this episode 179.
179.
On a little system called GPSS. A horrible programming system.
I don't know if I call it little. It's pretty expansive if you read all of the documents.
An expansive eldritch horror, which you know is one of the things we love over here for doing flowchart based programming, but it's only text and it's positional. So let's go. And yes,
well, it's not for flowchart based programming. It's for discrete system simulations. And it happens to use a flowchart as the central metaphor for what a programming language should be.
Right, because again, you're right. It's a flowchart metaphor, but you're not drawing a flowchart. This is the 1960s, and you are writing. I mean, you're effectively, it's a positional language. We'll get to it, but you're filling out a punch card, and these slots mean this thing. And somehow that also corresponds to a flowchart. So anyway, as Sean said at the top, because we were just talking about this, we're just making this the theme of this show, and we're going to try and say it every time. Our theme is, what's a language? What's an OS? What is a computer? And what does it matter? Are they all the same thing? This is our exploration in this series.
As far as like a meta-narrative of advent of computing, those are kind of the central questions that keep coming up over and over and over again.
I mean, that's what makes computers cool to me. You know, that's like the thing is you keep this. It's a big history of people discovering the same goddamn thing over and over and over again in different interesting ways.
When people ask me like why I get really interested in certain things, I'll always be like, oh, it's like a fractal. You just keep looking and there's more stuff to look at.
It really is. And
it just spirals around. And it's super neat. And if you zoom in again, there's more. Look.
Oh man. Okay. Also, because now I'm looking at my notes, I've already gone off script here.
Well, that's how we do it. That's how it starts.
That's how it starts. That's how we have our fun. The original intro was supposed to be, welcome to Widget Co. Come in and get out of the rain. Because that's the virtual setting of Sean's workplace.
It's my forever example. Widget Co. makes everything, which makes it a really good example to use for everything, you know.
It's the everything company. Also on my notes for the intro is we got to mention, and I feel like anybody who watches the main show, this after show, is vaguely with us at all, probably knows Usagi Electric at this point, because he's like the guy. He's the new the guy, and he's great. And I have yelled at him at VCF East, and he was nice.
I mean, you should.
I did.
Dave's very nice.
Yeah. And, because of course you've probably run into him a few times. I mean, you said you're on his Discord and stuff, and obviously.
Yeah, I've only ran into him once at VCF West, or VCF SoCal, when he had his LGP21 there, which is the only... I didn't know he had a YouTube channel. I'm just like, that's a cool computer. Would you like to get a beer and talk about that computer? And he's like, yes, actually. That sounds great.
Especially in a small community like this, that's the best way to meet people, is to not have any clue, and then you run into them, because that's the way it works with these kind of niches, right? Is like you don't realize that somebody is like a person, because like being a person is like you have several thousand people who know who you are, and across the whole world of people, that's nobody. And then you find out they're a person, and like you weren't worried about them being a person, and you just got right into the nitty gritty of having a cool conversation.
So the point you were getting to, though, is Usagi's finally doing the LGP21 restoration.
Out. Yeah.
Which is exciting.
There's that. He mentioned you on the show. He mentioned you on the show. That's the whole point here that I have been avoiding.
It's because I've been bugging him, because he's doing the LGP21 restoration finally. That's one of my favorite architectures. It's no secret. And he's dumping the contents of the disk memory because it's non-volatile memory. It has whatever was on it last time it was used. So that I got to see a little bit of the data from that so far, and I don't know what it does, but I'm excited to see more code spit out of it.
Yeah, so that's rad. That's just cool points to you, and me as a vicarious sidecar onto that I was mentioned on Usagi by I had a person that I talked to on a bi-weekly basis. Mentioned on a YouTube show.
Was mentioned on a TV program you watch on weekends.
There we go. Now I'm famous. All right. So
you made it.
Let's get into it. Let's get to the actual topic, which, I mean, again, we've done a few of these now. We know we're barely going to talk about the actual show topic, and that's okay because this is about the ancillary stuff, and that's the fun. So, I mean, we're getting back into, this is where we came up with the phrase in the first place, the what is a language, what is an OS, what is a computer, because that was one of my first subjects that I wanted to get into, and my subtitle on this one was, God damn it, it's all coroutines again, because it just reminds me of, we'll clearly, based on this list of things, get back to it some more, but it's kind of like the situation with RxX, where it's, you've got some kind of execution environment, and it's also, in this case, it's a language. And I mean, like, gosh, as I'm talking about it now, you talk like Lisp stuff, like Lisps kind of can just become OSs because they are sort of an execution environment. You end up with
it has memory management. It has so many other things you need already.
And like maybe a thing that you can do to spawn off a task, or some other routine. A lot of that stuff. Smalltalk very specifically has, and Smalltalk obviously massively and inspired by something like Lisp, but Smalltalk is essentially an operating system when you get down to it, but it's also a language. And this stuff just keeps coming up over and over and over again. And to me, one of the first things that popped into my head is it's always coroutines. Everything's coroutines. Just because that's
or child processes, or forks.
If you so often exactly, like you just keep running into this issue of I need to maybe execute a couple of things at the same time, or kind of at the same time, or I want to model it in my head as being at the same time, or I don't care if they're running in parallel or not.
That's something I didn't really get into on the episode. If you go back and read the GPSS history paper, the author spends a whole lot of time talking about simultaneity of events.
I already love it.
There was a lot of research that was done in developing GPSS so you have your flow chart of blocks that transactions flow through, and that's the model it uses for discrete simulations. But what happens if you have two blocks that should happen at the same time step, and you have two transactions that hit those blocks at the same exact time? How do you make sure the model treats those as happening simultaneously, even though it physically can't process those two things at the same time? Because computers at the time were inherently single process executing. They aren't multi-core or multi-threaded.
And so that's I can't remember if we said it while we were recording or not, but I'll say it again. The thing that I said, where I find computing, and especially historical computing, so interesting in large part because you find it to be the story of people discovering the same thing in different ways over and over again. And so it's like,
and having different insights into the same thing.
I mean, it's kind of the mathematical beauty of, and I love the idea of math. I'm not very deep in as a math person, but
what's a percentage, right?
Yeah, but it's that the fancy word isomorphism. There's a math term that I was going to bring up, but that in math that you keep finding that the same situation raises itself over and over again in different applications. Like you come up with a formula and you're like, wait, that same kind of growth happens in this completely other
There's a certain
thing.
symmetry to a lot of mathematics that you can run into. I know for me, since I'm a physics head, physics is all about symmetry when you get down to it.
Right.
And so there's a lot of problems. Like, for instance, I assume everyone's been watching the Artemis missions.
Of course. How could you
not? Right before we started recording, they just pulled the astronauts out of the pod.
Yeah, I mean, I'm obviously into it, but I keep coming to it like a day late. So I'll find out about that tomorrow.
Well, the live stream's over now. It's too late. But so thrusters, right? They have to throw mass out one side and it makes the rocket go forward in the other direction. And there's a symmetry there. The same with like that. I keep seeing this one photo where there's a bunch of stuff floating around in the capsule, and one of the astronauts like puts down his eyeglasses case and it stays on a table, and people are like, oh, well, why isn't that floating away? It's like, because there's nothing pushing it. So right. There's a symmetry where nothing's pushing it, so it's not going to move. What I'm rambling towards, though, is there's all these systems like physics, like math, like computing, where there's a kind of symmetry, a kind of like rhyme between a lot of different aspects.
Ooh, rhyme is a great word. Rhyme is an awesome word for that.
But that's kind of why, at least in my head, we'll run into like, oh, hey, here's a programming language that, well, to write it, they had to write a memory manager. And isn't that kind of like an operating system? Or, well, here's an operating system. It has to have a memory manager. You could use that as a memory allocator for a programming language.
This is I can never get over just any garbage collected language, and the kind of funny aspect that like you're managing your garbage and then your operating system is going to manage that garbage. You know what I mean?
Well,
like when your runtime exits, it doesn't matter whether you collected it or not. The operating system still has to collect it because it has no idea. So you just got like 2 layers of garbage collection going on there. But yes, so let us get to we've come back up the garden path here to we talked all these symmetries and rediscovering things, because you were talking about I really liked, because that's the first I'm hearing of it, that I mean, how could you not obviously have to think about operating things in pseudo parallel, which is what is that, Sean? That's multi-programming.
Yeah, that's
but this guy wasn't trying to solve multi-programming. Right.
No, he was specifically trying to write a general purpose tool for discrete system simulation.
Yes.
That on the surface, that doesn't sound like, oh, I'm going to write a time-sharing system. I'm going to write an execution environment. But that's exactly the same problem set. You're solving the same issues. Yes. It's that weird macabre symmetry where everything's almost the same. What's an operating system, Joe? How is it not a language?
How is it not a language? Now I'm going to take a hard left, because I think, again, we talked ahead of the episode and I knew we're going to just keep coming back to this topic, because I think with languages especially, it's just coming up with abstractions, because languages are made to solve a particular set of problems or a particular domain of problems. But as you said, and we'll get back to
the right word.
They're all Turing complete. Any Turing complete language can do any other Turing complete language. So anyway, it's all the same thing. So let's take a hard left so that we can come back to that later and talk a little bit about positional syntax in early languages, because
oh my God.
Go to Wiki, folks. I listened to this episode and mostly wrote down notes of like extemporaneous stuff that occurred to me, but is not directly about this language, GPSS. So we're going to have a lot of chat about that. But then I went to the wiki page, because I was like, I should probably do some research on this, because I didn't really this time.
Just trust everything I say to you. Everything I say implicitly do. I don't make mistakes.
That's why I listen to the program to give up my decision-making abilities and just ride the wave of assuming that you're right. But yeah, oh my God, the syntax is atrocious.
Oh,
I mean, it's kind of super simple.
Well, it's super simple, but it's super impossible to read. So I had that whole digression about how if you look through even a primer on GPSS, you don't see any code until like most way through the book.
Mhm.
And I think there's like reasonable explanations to de-emphasize the syntax, right? You're just describing the flow chart. It's supposed to be used as a tool, not as like a programming language in and of itself. But also the syntax is just disgusting. And if you lead with it, go look it up. It looks like you filled out a spreadsheet. And if you just handed that to someone, you're like, we're learning GPSS today. Here's a spreadsheet. Their eyes are going to glaze over. They're going to like pass out. They're going to lose blood pressure.
And this all
because
goes
it doesn't
back
look
to
like a language.
No. And it all goes back to, again, listener, it's punch cards. That's what positional languages are about, because a punch card they could be anything. Punch cards, I mean, let's go ahead and assume that people are tuning into this show because they would like to know more about old school computing and maybe don't know as much as we do. Maybe we have a tendency to assume that people know. So I'm going to go back to the punch cards are not a computer thing.
They're just a data thing.
It's it's for, I mean, particularly like the IBM format that we're aware of. It's it's a way of storing text and 80 characters of it, and that's what it's for. And so you get a bunch of these languages in the early times that are positional, which is, it means each like set of, however many columns of text are fixed to doing a particular thing. It is like you said, it's like a cell in an Excel chart, and this cell means this thing, that cell means this thing.
Characters wide.
Yes, because that's how big your card is.
So the most similar syntactic language I can think of is RPG, which does the same thing where the language is just actually filling out like a couple spreadsheet forms. Somewhere in my office or in the rafters above me, I have some old RPG programming sheets, and it is literally you fill out a series of forms and then submit that to a cleric. And you're like, please, sir, put this in the computer.
And GPSS, when are you going to burn those?
Never. They're a relic.
They're a relic
but
of a more
GPSS,
horrible time.
Exactly. This language has the same kind of vibe where you fill out a series of forms, and that's your code somehow. But it's the weird thing, like what trips me up about this, and you were mentioning this, I think off mic, Fortran, right?
Yes.
Fortran is also constrained by 80 columns.
Well, that's because I asked, isn't Fortran another one of those positional languages? I thought Fortran was positional.
Kind of is, because there are certain columns in the beginning of each line that are positional, like comments. If to have a comment in early versions of Fortran, the first character has to be a C. And I forget what all of them are because I've only ever used C for comments. But there's like the first 3 columns each have positional meaning, and then everything else is syntactically meaningful. But then you have other languages, like I'm learning some more Snowball 4 right now. I forget who recommended this, but someone said, hey, Sean, you should get this book called Algorithms in Snowball 4.
Brilliant.
And I was like, ha, 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 that sounds horrific. And I looked it up on eBay, and it was actually very cheap to get a copy.
That's the problem.
Oh my God.
Niche knowledge, man. Nobody wants to buy it. So it is out there for a low, low price.
I'm into like the first couple of chapters. It's a very, very charming book. It's typeset in ASCII, so it uses ASCII art for everything. And it was typeset using a Snowball 4 program that's an example program in the book.
Now,
so
it doesn't get more programmer than
so
a
cool.
meta self-referential book.
Snowball isn't a positional language, but it has specific fields that you have to fill out, right? So each line is 7 possible fields, like slots that you can put little groupings, little tokens in, but each one's optional. So it's not, hey, go fill out this form for me. It's you have to write in this very specific way, but it's not syntactic like something like a C or a Lisp or even a Fortran.
There's the most minimal possible modicum of parsing.
Yeah, it's almost like there's it's not, well, almost like there's kind of a spectrum between having a rich syntax in like I'm thinking of maybe Lisp, but maybe more like Perl or PHP, where there's a really complex syntax that has all kinds of different like quirks to its grammar, and it's super contextual and really
lots of interactions.
Detailed. And then all the way on the other end, somewhere in the middle, you have like C and Fortran, you have Lisp somewhere. But then on the far other side, you have things like Snowball, and then things like these positional languages where there is almost no syntax besides which form field did you fill out.
Yeah, there's a range, and it's interesting to see that evolution programming languages. It's something that I would love to know more of the history of, to see that like timeline of.
I'd love to know if there are any modern languages that are positional, because it's not like a trend in programming. Like there's not a name for it, because RPG just says you fill out a form. It's a language. And GPSS just says it's a table-oriented programming language. So I haven't been able to find like the right term to be like, I need to find this whole family of syntax
and
style.
Especially when you're looking at early evolution, like there's not, everybody's doing it differently and coming up with their own stuff in their own way. So there kind of is no consensus like name for we're doing this or we're trying out this thing, or yeah,
exactly. It's not like not like
I
someone
needed
in 1954
this and that's what I did.
I
might have a name for it, but
this language was made as a rebuttal to the Algol 64 paper 12b, and you can tell that the like typeless syntax blah blah blah, people don't write that way until like way later, which does makes it kind of Wild Westy to try to look up information or try to track down information about early languages.
But isn't that the fun? I feel like for you, that's
really
got to be the fun.
No, it really is.
And that's, I'm just now realizing, finally we're having an episode that's about a programming language. And I mean, but not that we're very deep into these episodes, and you do a programming language like once every like probably 4 or 5 on average at least.
Yeah, that's about right.
But I mean, we're both developer adjacent. We live in that world kind of people. So I've just kept forgetting until this moment that I've been looking forward to talk language stuff, because especially it's because you brought up Algol and just that like I didn't realize how much everything is Algol,
everything's
like everything that we've got.
Algol.
That's also true, but that like most of the languages we're used to today are Algol, like they're their own thing now at this point, but I didn't realize the extent. And that's not what this episode is about, but gosh, I would love to talk about that more. I'm excited that we're talking about a language. So yes, positional syntax. I think we've covered about all you and me could ever want to say about positional syntax. But
I plan to say more eventually. It's just a matter of, like I was saying, it just kind of shows up like on my desk occasionally.
Oh, it's one of those.
Yeah, I don't know how to go out and find it. I'd love to go spearfishing, but it is just like, oh, we're doing tables today. All right.
Cool.
Let's go.
All right. Now, this is kind of worked out because I wanted to take that left turn and get off of the isomorphism talk that we'll get back to. And the next one is also off that topic too, so that's great. You lead the episode talking about how the reason this guy is building this flowchart table-oriented language is because he was involved with simulation stuff and analog computing as part of that topic.
Just to be clear about the analog thing, because it is explained really explicitly in the History of Programming Languages paper, he isn't writing this because, I always loved analog and I wanted to carry analog in my heart every day. He explicitly says, I think this affected me really deeply, and I'd be lying if I said it didn't influence everything else I worked on, but it wasn't a conscious influence.
Gotcha.
It's more like a mind virus. Yeah, I really like that paper. It's a weird paper. It's very introspective.
I didn't look at it. I'll have to go back to it. But yeah, that makes me wonder.
Hopple 1, the ACM History of Programming Languages, is on archive.org. And
all the good
ACM has it open access now.
Nice.
So you can just read it online.
That is wonderful. So yeah, I almost wonder if like we're putting now this perception of it being a representation of discrete programming as analog programming that like wasn't his intention. That's kind of interesting.
Well, I think it's fair to point out the comparison because the author literally does. He's like, yeah, in retrospect, there's some connection here. I didn't mean for it to be there.
But it's pretty obvious.
It's pretty obvious.
Looking back on. All right. Okay. So I don't feel like I'm putting an idea in his mouth or words in his mouth there. Then that's good. So without further ado, talking about analog computing then, because that's another one that I've wanted to get into because it's an interesting topic. And again, another one that like, unless you are interested in digging into that topic, you may never hear about analog computers at this point these days. You might not really know what the deal is.
Insular.
Yeah.
The information on analog computing kind of stops once analog stops being a thing. So it's...
Yeah. And it kind of becomes
irrelevant or hat. Yeah, it's something... The way I look at it is a lot of... So like when people say history is written by the victors, that also means like victors in an abstract sense.
Yes.
Right? So we get all these histories of digital computing because that's the winner. But analog isn't, kind of. It's more complicated than that.
Right.
But so it's not really discussed very much anymore.
But it was great at simulation.
It was great at simulation.
It's a real-time analog model. There's one is the realization at some point that if you didn't already have this obvious realization in your life that analog, analogy, it's all the same root, and analog literally means you're using something as an analogy for something else. And that's it.
Exactly.
You're using a magnetic signal as an analogy for pressure waves. And that's tape on a thing, but that it's using something as an analogy for something else. And that's literally what analog is.
It's direct, and early analog computers are modular. So it's really visceral. That's every time I read about electronic analog computers, there's always like some aside, even if it's a super technical paper, where the author will be like, and these were just really nice to work with. It just made sense to use an analog computer. Because you could see the line move, you could pull wires out, you had components you could point to. And so when you're building up a simulation as just, here's 5 blocks and I physically connect them, there's more of a connection.
I didn't know what a model was. It's a machine for making models, models.
It's a machine that is a model.
And that's why, so I put this in here, and I think we're really just going to speed past it, but I throw this one at you. Analog computer is a bad name for what those things are. I feel like this is just my silly opinion, and it's silly. I realize they compute, they do computational things, but that it's a systems modeling kit, or like, because it doesn't do, I think that's one of the things, I think this is where it comes from, is when I started understanding about analog computers, I'm thinking, okay, so they like compute in some sense in like the same way that a digital or discrete time computer computes. And it's not really, because you think of a digital computer as you put in something and it computes a result, right? Which is also kind of a poor way of thinking about it. And that's not really it's a difference in goals, maybe, to me, is that that's not really the goal of an analog computer. The goal of an analog computer and what it's good at is to be a dynamic system. Right, so that it's a constantly changing influx thing.
Well,
and
interestingly
you're modeling
enough,
things that are, again, I'm not a big math guy, but that fundamentally things like
a pendulum on
differential equations kind of things, right? Where you've got it's multiple variables influencing each other dynamically over time, and that's what they're doing. They're modeling that kind of situation.
Now, when you first said oh, analog computer's a bad name. I thought you were going to say analog and be like, well, it should be called continuous.
Oh, that's pretty good too.
It would also work. Mm-hmm. I think analog does fit better. Like to your point,
because now we've had the discussion. Right. I was going to say now we've had the discussion about an analog means analogy.
Analog computers were called computers before digital computers.
Now, see, that's interesting because I figured that would be kind of the place I'd get called out.
Be called that.
Yeah.
Yeah. We call them number boxes. Discrete number box.
Yeah, hyper complicated switching networks with numeric
I'm calling
result.
Mine AT&T. AT&T in a box.
Okay, I like that. We can bring that part of the chat on. I think the name is wrong. Back for a full circle because I like you put that back on me, and now I am the fool. We shouldn't have named digital computers computers. We should have called them discrete number crunchy boxes.
Suffering containers.
Love it.
But so yeah, that's going back to the topic at hand, right? GPSS. Yes.
Sure.
Because it's this modular system where you have a series of these blocks that operate on transactions that represent like a signal flowing through this network of modules.
Right.
It's conceptually very, very similar to how analog computers work.
Yeah, this box does a multiplication on it. This box sums two things. Each one has a job. Especially
since GPSS is designed for simulation and analog computers are designed for simulation. Going back to the symmetry, there's a really like clear symmetry there. They're super, super similar tools. And also, if we want to talk symmetry, RPG is developed in the same period, roughly, as a tool to make it so you can treat a computer like a punch card tabulator. So it's another,
and it really is, It's turning a computer into another tool, like
it's these
like
weird
expensive typewriter
tools, exactly, to make your computer act like something that you're more familiar with.
Which, God, if that's not just how we use computers in general these days, I mean, that's why computers are
skeuomorphism.
Yeah. It came, it went, it came again. It went again? I don't know where we're at now. Yeah, I just wanted to plug in there because I don't have a good place for it otherwise, but to shoehorn in just a little bit more basically unrelated analog computing stuff in, I just want to say one of the things that I love about analog computers, and maybe I'll get into it more in depth when we like talk about an actual relevant topic sometime, is just that if anybody out there is like musically inclined, a modular synthesizer is an analog computer. It's that's kind of where they come from. And I think that's also a very interesting thing in like this technology diaspora where that's a lot of what we're talking about in the digital computing world is our subject, but there is just generally like technological diaspora. And that's one of them is like, it's lab equipment. It's a simulation computing system. Oh, also you can do music with it. And it's symmetries. Man, human technological history is it's a thing that keeps happening, huh? So
I talk about networks.
Networks. Well, I'll talk about a network, which is that the next topic is computation as a signal network. And that is awesome because you accidentally kind of got us there a minute ago.
Perfect.
Because you used almost exactly those words talking about the network
I know
between
exactly
the boxes.
What I'm doing.
Of course, at all times. And as we mentioned, my brain is turned off. I'm coasting. So computation as a signal network. We're finally back to the isomorphism thing. And just every time we talk about a language, we're going to talk about how everything is everything else. And I was saying before the call that I'm probably going to take a bunch of lead on this one because it's just something that occurs to me and that you said you don't have as much familiarity with. And that's like, I see this as kind of an analog to functional programming, this sort of thing. Which, when I look at an analog computer as a transition off the previous one, I kind of see the same model because that's kind of how you want to think when you're doing functional programming is you are not describing the steps of things. You're kind of describing this plumbing model of data comes in one side and is transformed, and that you can
more about
equally
talking about the functions that do things to whatever the inputs are.
Right. And I mean, that's it's so funny that it is not even, it's a punch card language it's trying to make a computer into a flowchart interpreter. But isomorphisms, what is a flowchart if not? Let's think about a flowchart this way. This was a way that I liked to think about it when I was going into this, is what is a flowchart but a pipeline where your state is the thing going into each functional unit and being transformed and being passed to the next functional unit, right? That's just the core idea of functional programming. And that's what a flowchart is. And you can think of it as doing steps, or you can think of it as transforming things. And it comes back to that.
It's almost like because of the Church-Turing thesis.
The Church-Turing thesis.
Turing complete is actually just everything else that's Turing complete.
That's. I was trying to think of Church-Turing thesis. So thank you for throwing that in there, because you read my mind. But that's exactly what it says: is functional programming people are always, they love the idea of the lambda calculus. That's Church's thing, and other people, they know about Turing machines, and there kind of always has been for programming. I think like these two worlds where there's people who really think of it in terms of they're like way into the lambda calculus, and there's other people who are just way into like, I know Turing machines.
Well,
and especially
I'm
people who are
guy.
not even that.
I cannot explain lambda calculus to save my life.
It's so good.
I can explain a tape though. Goes backwards and forwards. Zoop, zoop.
It's an easier to understand paradigm for sure. And it's funny that I keep saying that I'm not really a math guy. It's that I wish I was
lambda calculus.
Right, because
I don't know math.
Man, it is cool. I think I like it especially because it's one of the few. I mean, anybody who's seen anything about functional programming and lambda calculus, you look at it and you're like, that is mathematical weirdo horse shit.
Yeah.
Like, I don't understand. But then when you, like, the fact that I was able to pick it up, and anybody can, and be like, oh, wow, your mind like suddenly turns around and you see how things work that way. It's just such an interesting thing for your brain to see things from a different aspect. And as a non-math guy, now that feels like I'm doing some kind of interesting special math.
I should actually learn about lambda calculus.
You should, but then you'll become one of those guys, because I did. I'm
already one of those guys in so many regards. I think I'll survive.
Well, when I originally asked you, that was the thing. I said either you're either gonna really be into functional programming, or you are going to not at all be into functional programming. There is no in between.
I'm such a big object-oriented programming guy that I've had coworkers get mad at me. Because I have some coworkers that are really big into functional programming, and they're like, Sean, you should write your code this way. It's so much better. And they'll be describing something to me, and I'm like, yeah, it's just a class. You're just writing a class. You have
isomorphisms.
Isomorphism. Oh,
that's my fancy math word.
That's just a class constructor. You could just have a class. There's nothing stopping you.
Oh, us being off in the weeds. Don't use the word currying with me, because it's going to remind me when I tried to explain currying to my coworkers in like a
it's just a function. Easy.
Yeah.
So is a constructor, straightforward, technically.
So yes, that was the topic was computation as a signal network, because that's kind of what this is. Because what is a flowchart but a signal network? And that is isomorphic with so many other things. And it also made me think of Scratch and Lego Mindstorms, just visual programming. Because again, I like that we clarified up top. I really appreciate that you set that aside for us to remind us that there is no flowchart here. You're not drawing a flowchart. It's the concept of a flowchart.
Yes, you can use a flowchart as a fun tool, but at the end of the day, you fill out the form and give it to the computer cleric.
It only exists in your head. And
it's the theory building is visual.
Yeah, because all I could think when you were talking about these blocks and the transactions being passed between these blocks, it just feels like visual programming languages. And it's on my mind because I have a young kid I'm trying to get him interested in not even interested in programming, just expose him to the idea of programming, because
one must. It's important.
We inculcate our children and they cannot escape it. But yeah, so I'm just thinking of, oh, that's just like Scratch. That's just like Mindstorm. It's just like visual programming. And it is funny because it is not. There is no visual element here, and yet it is conceptually.
You also got to be careful because flowchart programming is just one possible avenue for visual programming. There are other ways you could do it. I don't know other ways that are as big.
Come up with it. Come up with it right now, Sean. Come up with a new way. No.
Oak tree. We're doing lists with 3 pointers.
Next topic.
Okay. All right. Let's
Hit
go.
The bricks. Well, here's another one that's also probably going to go off the rails real fast or not go very long. It was the origins of OOP in this kind of simulation paradigm, and it carries on in the isomorphisms thing because again, we can carry right on from you talking about functional programming, which I compared to this idea of stuff flowing through a flowchart. They're all relating to each other, and you're saying to your functional programming friends, "Oh, well, that's just
you've reinvented a constructor.
A constructor. Yeah, you've invented a constructor." Which, because I'm sorry,
I'm using lambda calculus to invent a table from first principles. Get ready.
I don't understand how I can't describe to people that a closure is just like you made an abstract class or a anonymous class, and it has a field in it that's carrying along. And because that's literally what C# does.
Or an actual class. You don't have to be anonymous.
But it's isomorphic, damn it. God, I'm gonna be clipping the whole time that I'm editing this. Just yelling into this mic. This means it's a good episode.
Pump it all the way up.
So yes, OOP. And its relevance here is
programming. In case anyone it gets confused by us saying OOP, OOP, OOP.
I apparently. I think this is more of an India thing because I was interviewing a good number of overseas Indian candidates recently, and they refer to it as OOPS a lot, which I very much enjoy.
I like that
because they call it object-oriented programming systems or something like that.
A lot,
and so you end up
actually.
with OOPS, and I really like OOPS.
I'm going to start using that at work and really upset my coworkers.
Excellent.
You're using curry.
Lean over their shoulder lean over their shoulder with a coffee cup and go, oops. Just point at our work and say oops. Anyway, yeah, I don't know what the tie-in is on this one is, except so there's an explicit tie-in, but then I don't know what we have to talk about on it. Just that it makes me think. I keep always referring back to the Smalltalk 80 book because it's one of the first books that when I decided to realize, oh hey, you can just get academic books from the library or monographs, you can just get them from your library system and read a monograph.
Those kind of guys, you're coming out as a Smalltalk 80 kind of guy.
I don't even I like Smalltalk 80, just Smalltalk in general because it's weird because of course it is. How could it not be? But to try and rein me in, the point on the Smalltalk thing is that you talk in this about that GPSS was used a bunch for queuing theory and queuing simulation stuff.
Yeah.
And that's neat because apparently
I think maybe
neither of us have heard that much about queuing theory outside of this. And we both independently heard stuff. And I was like, wait, but I heard about queuing theory because they make there's a whole volume in the Smalltalk 80 book, which is why I'm mentioning it, that is about implementing a queuing simulation using Smalltalk because, hey, it's a really good, you can represent, resources. That's an object and it passes a message to another thing. And which isomorphism.
Well, Smalltalk is about message passing, which if you want to have some way to simulate a queue, you're going to have messages.
Yeah. And now is your transaction in GPSS, is that your object? And then your block is your message that you're executing on that object? Kinda. I mean, one can think of it that way.
I think the more direct way, if you want to take that line, is the transactions or messages, and the blocks would be I guess they're not quite objects because
yeah, because I think of it as like the object is the part that
objects.
Maybe it's because I'm such a C programmer, and so I always think of objects just as structs, and so like the object is the data, and then it is associated with methods, but to me the object is always at its core the data, because the methods are just functions that take a reference to that data really, and your function always stays the same.
Homie's not using inheritance. Objects inherit.
Oh boy. Okay. All right.
I'll stop.
Oop FP. Oop FP.
Oops. But yeah, it is very much. We should just learn. I should just learn more about queuing theory.
Yeah, we gotta, because that's really the point here, is that neither of us have ever talked about queuing theory, and it comes up here in this simulation language, over in the Smalltalk book. And I know they talk in the Smalltalk book, and I heard a little bit like surrounding that from God knows where, that's a lot of what Simula was trying to do too. Like there's a lot of queuing theory in why they came up with Simula. And of course, Simula is the granddaddy of C++. And I mean, a Smalltalk was inspired by Simula. Every object-oriented system is inspired by Simula, basically. And it apparently all comes down to queuing theory.
I didn't know that connection. That's weird, because the reason GPSS uses or talks so much about queuing theory is because it's developed at IBM to be used to describe IBM systems that include like waiting around for a disk drive in a queue.
Ooh,
right?
Let's get to the topic. I'm getting back to the core thesis of our show, which is what's an OS, what is a language. This is also a perfect place to get us there. What is an OS? What is a language? What is a computer? It just occurs to me. You're talking about they're using GPSS to do queuing theory to figure out best utilization of an IBM computer system, right?
Yes.
Is that not the job of an operating system?
Yes, Joe, that is the job of an operating system. Very funny.
I'm sitting here thinking as we transition into this, because you don't realize what's in my head. I'm thinking about GNSS or GPSS makes a great basis for an operating system, because it is a like task execution model, which that's like we talked about in the RSX episode. That's a big core of what an operating system does. Is its job is the tasking model.
Tasks. It keeps things isolated. But it allocates resources. Time is a resource, actually.
Yeah. If your language has some kind of threading or coroutine system or this sort of that's a tasking model system. And now you've got part of what makes up an operating system. But I wasn't thinking of in why you would do GMX, that aspect of like resource management and like optimizing resource utilization, which is the other big operating system thing, because of course that's your IBM batch job kind of thing, where you're manually trying to decide which jobs should be submitted because they will optimize things, and then you write a program to optimize that, and then you've got GPSS over here that's, hey, let's write a simulation system to simulate us submitting jobs to things so we can figure out what the best way to is. And then you just do that as part of your it is the operating system. It figures out the optimal way to do it.
The simulation is in fact the operating system.
Right.
Yes. Yeah, that's so I said it on the show, and I'll say it again. I really, really want to find that IBM technical paper on GMX, because I have so many questions about the implementation. It's at a period where operating systems are, like you were saying, instead of hand optimizing batches, you have now programs that optimize batching, or you have a program that can supervise execution of batches.
Well, it's like that same like obvious when you get computers, you realize, oh, you can use the computer to figure out stuff for the computer. Oh, we could hand assemble this written down assembly into machine code, or wait, we can make the computer assemble the assembly for the computer. Yeah, it just keeps happening.
But I'm really, really curious if GMX was actually if it was interactive, because it says in the History of Programming Languages paper, which is the only thing I can find that says that GMX existed, it just says it's a real-time monitor. And that could mean like we were talking about with RSX. That can mean like 10 different things.
Monitor is such a loaded friggin' word.
Yes. Yeah. Is it in my ears? Is it in front of my eyes? Is it in my heart? Like, what is this?
Does it let you examine memory? Does it let you dispatch whole jobs? Like, it runs that gamut.
Does it just mean it's a thing that supervises execution? Does it monitor execution? Or is it something you type into that's interactive that handles execution and multitasking?
And then don't get me even started on the unrelated topic of, I don't even know if anybody uses this as a concept anymore, but monitors in terms of like mutual exclusion. Because I didn't want to use the word mutual exclusion because mutexes are a particular thing that also solves this problem. But of like critical sections, there is a thing.
Yeah,
I would think that you're maybe aware of monitors as a concept, which is basically like it's like a block of code or a structure that is the critical section, or like you can have a class that's a
critical
monitor.
Sections and mutexes and locks. I haven't come across monitors before though.
Yeah, well, it throws one for a loop because it has nothing to do with what we're talking about, but it is. There's a thing called monitor over there, and it's in my head because I'm reading one of Andrew Tannenbaum's books right now is my fun read. It's Modern Operating Systems. That's a hoot. Whatever you think about Minix, Andrew Tannenbaum, as an aside, go read an Andrew Tannenbaum book because he is hilarious. He is just so, I want to hang out with him. He seems like a sweet guy who just takes everything like kind of tongue in cheek, he's completely unserious about all this stuff. And he's
send him an email
writing operating systems and having arguments with Linus Torvalds and stuff. And he just doesn't take any of it seriously.
Sounds
like
a fun career.
He sounds like a cool guy. Anyway, that's why overloaded use of monitors is in my head. But yeah, so a thing you said in there was that you couldn't find like anything, barely anything about GNX, even GMX, not the album, GMX, not GNX.
The theoretical operating system.
The theoretical operating system that you you barely have any documentation that it even existed. Yeah. Because a question that was running through my mind here was what the hell did GMX even run on? But if you don't have that answer, you're not going to know. So I was curious
ran on
because
7090. It ran on an IBM 7090. So it's a mainframe.
Sorry, is that where you were saying in the episode GMX was running on the front end machine?
No, so that
that's where I'm getting confused.
Yeah, that is confusing. So the example of having a 7040 to monitor, there it is again, to monitor execution on a 7090, that's a case study about how to use GPSS to simulate a system.
This is a thing you could do.
This is a thing you could do, and it's a thing you can buy from IBM, and we have a model about it. Get bent. We filled out the forms correctly. But GMX was developed on a IBM 7090. So it was on a big iron. So it had power. And we do know that it did multitask and do context switches because it put context data on transactions.
Right.
So it used a transaction to model a process, and that had full context data, enough to do like an actual context switch just on the transaction that's flowing through like these loops, which is wild to me.
I mean, when you've got a hammer, everything is a nail.
Yeah.
When you've got GPSS,
when
everything is a GPSS
task.
Everything is a transaction. There we go.
It's such a funny concept of like, here's my programming language. Yes, you do have to fill out the form and hand it to someone in a machine room. Yes, it is actually a flow chart. No, it doesn't have lines. Yes, it does have blocks.
The like levels of translation here in that you come up with your task, you turn it into a flow chart. You turn your flow chart into a form. You submit your form to be processed
to someone who then puts it on punch cards.
Now, this is the most 60s computer room thing that I've ever heard. Now that I'm thinking of it that way. Good Lord. You're probably doing your flow chart crazy. As you're planning this thing out using those little stencils. Have you ever seen? I'm sure flow chart stencils.
So what's really funny in the IBM Systems Journal articles on GPSS, it builds up the whole flowchart lexicon for it.
Nice.
And so it has its own set of symbols, which are
it would be because that's IBM. I mean, they've got
very IBM.
Because I mean, you look at wiring charts and whatnot. Love the IBM wiring charts when you're trying to figure out like how does the architecture of this thing work? Because it's not AND gates. It's IBM layout, and IBM it looks like nothing 12. Else. But it is a IBM standard. God damn it! And it is the standard they use for everything. If you're in IBM,
wear a blue suit.
It is well defined. If you got a blue suit, if you do not have a blue suit, you will never have seen this in your life, and you never will.
I just need to start going to VCFs in a blue suit and just concerning people.
How is that not a thing? That would be like the perfect cosplay. If we ever end up at a VCF really together sometime, we should do that. I would 100%.
What we gotta do, I'll dig up. There's some papers from the '69 antitrust lawsuit that include accounts of people's IBM reps showing up in blue suits and like crying and begging and pleading and doing like all kinds of weird, uncomfortable things to make people keep their IBM account open.
I mean, you don't want Big Blue to go out of business. They're just a small mom and pop, you know. They need it.
Yeah, if you, I'll fall out of the sales club if you don't renew this contract. I won't be able to buy my son his first car.
God, reining it back. This is the theme. Reeling it out, reining it back. That's the give and take. And what is a computer? Just bears mentioning. I mean, we've kind of already covered it, but to put it into words, I just like with the GMX thing that considering the first episode that we did together was the one talking about RSX, and it went through a very similar thing where it's just like, we've got this tasking model. We've got a system that executes tasks for like a totally different reason.
And then you can do a task that takes input.
Yeah. And
why don't we do that?
Plug it in. Now it is an operating system. And that I would not have expected that parallel to just come out of the blue. And I loved that as an ending to this episode.
Well, I think it speaks to flexibility, right? I said in the episode, if you're a programmer, you should think about writing software that's modular and flexible.
Right. And if you're a programmer, you should probably think about writing it in a functional style, is what we both agree on.
Or oops. You should consider oops.
All right. I think we have. I forgot to set a timer this time, so I have no idea how long we've been running. It might be long.
We're doing great.
We're doing great. All right.
It's 58 minutes.
Oh, that's just on time because I was going to say, I think it's about feeling time to me to hit this last bullet point, which is the any cool stuff we missed bullet point. So, in the last couple, I've kind of done an outro of like, so Sean, is there anything that you want to talk about on this that we didn't talk about? And this is basically the same thing, but I want to phrase it as any cool stuff we missed, because I feel like that's more inclusive of like anything you would possibly want to say about this, or not even just stuff that was in the episode.
We've covered, I think, everything that I think about GPSS. It's just weird and very, very different. And I'm gonna blame my man Dan Timken, another one of my co-conspirators, author of 44 SOLangs.
I was gonna say that's the SOLangs guy. Yep.
He said something to me about how the question of what is a programming language is very important. And in his book, he even says, I'm going to present a pile of programming languages. There will be at least one where you say, damn, that's not a programming language. And I will say, why not? And so that's been kind of living rent-free in my head for a while. And that concept is what makes GPSS so interesting to me, because if you look at it, it doesn't look like a programming language. It just does not. But it is, and it's flexible enough that you can write an operating system in it. Maybe we don't have the white papers, but maybe
it's
you can
flexible
write an
enough that
system.
Someone said you could write an operating system.
Yes,
in it
and had a citation.
Yeah. All right. Well, I think that covers everything, and I mean, just great chat as always, and
I had a great time.
Everybody. Look forward to your next episode of Advent of Computing next week.
And Adjunct of Computing.
And then Adjunct of Computing following that, because I just feel like every episode has been better than the last, and I am having a great time. So I look forward to doing
a blast.
I look forward to doing this with you.
That's what
next
means
time as
a
well.
podcast is successful. You have a good time.
Well, especially because I'm finally fully leaned into this podcast exists for us, and if someone wants to listen to it, then good for them.
That's the spirit.
Yes. All right, everybody.
I'm stopping recording.
I'm cutting it there. That's the perfect place to actually end the episode.